my slides.
Yes, we can see your slides.
Okay. All right. So, okay. So thank you, Kate, just for this invitation as well. And as you said, there was a very nice presentation of Thomas and Kathy a few weeks ago about the Glosis model. So there has been, of course, some other threads of work related to this, and that's what I will be talking now about the semantic representation of this model. So the Glosis ontology. So just a quick recap of the Glosis. As it was mentioned in that presentation, it's providing some kind of a special data infrastructure that brings together soil information collected by different national institutions. And it's envisioned as a kind of federation of different soil information systems. So this is like general, the kind of concept behind Glosis. And there was a consultation made by Thomas and Kathy and probably some other colleagues with the FAO, and this was also related to the efforts that we are taking in the project called CAU Soil. So they wanted to make a model for the soil, so soil data model for it's the Glosis data model, and this of course was a very large work because it required the modeling and interconnection of more than 300 soil properties that were just extracted from different types of literature and documentation and so on. So this was a very large work that they did, as it was presented in the last time. And so just as a quick overview of how this was the outcome of this work, was basically that we have a model, the data model of Glosis, that was implemented as a UML data model. So this is what we have available, or we had available at that point. Of course, the Glosis is based on the ISO 28258 about the soil quality. So this is like the starting point, as it was also presented. In there, of course, all the spatial objects types were describing soil objects plus the artifacts generated by soil sampling. Additionally, there was, of course, information about various observations or measurements of physiochemical properties on those objects. So that's like the core, let's say. And in terms of the actual implementation, it was defined as 9 different spatial object types, including like site, plot, surface, and others. And the information about those objects was mostly represented as using the observation and measurement model that also Kathy was describing in the previous presentation. So the idea here is that they used something that was called the container classes or container types that were defined to group different observations relevant for a specific spatial object type. And of course, additionally, they had some few extra attributes for spatial objects classes. So that was like the starting point. So that was what we had at the beginning. Um, and then, of course, the point was how we are going to be using glosses in our semantic world. And this comes because, first of all, in the CAU Soil project, we are implementing and testing a shared CINO EU web observatory platform that is providing open link data in order to monitor the status and trace of soil, and also to assist in the decision making to support agro ecosystem functions in view of the climate changes. Um, of course, I don't know if you are very much aware or not, but linked data is basically structured data that is interlinked with other data so that it becomes more useful through the exploitation of the semantics behind. Linked data is actually already one of the most popular methods for publishing data on the web because it has several benefits. First of all, it improves the data accessibility by both humans and machines. So the agents or applications can also understand what is behind this data and how the data is connected. So this improve the findability, the reusability, and the integration between different data sets. Additionally, it of course enables to discover more useful information, more useful data through those links that I mentioned, but also through kind of inferencing that we can also perform based on this semantic model behind. And of course, we can exploit this data using semantic queries, which is a very powerful way of accessing the data in an integrated way. So linked data, actually, because of that, large or very important benefits, it's a lot of data sets have been published already like that. So this is like you can see on the right, this is the Linked Open Data Cloud, which is an ongoing project that is all the time collecting and connecting different data sets from different types of domain in a huge knowledge graph, let's say. How we are producing linked data. So basically, linked data is defining a simple set of principles and technologies that should be used. This, of course, include the use of URIs to identify resources, the use of HTTP to exchange the information, to transfer information, use of RDF to represent the data, and use of, for example, SparkQL to query this data. And there are many different guidelines and recommendations how we can generate linked data, but one of the most important steps in every kind of those is the model specification. So we need one underlying model to use to represent the data in the semantic format and then of course put it in RDF and so on, but we need a model behind, of course. And this is what where Glosis comes into play. So in order to allow Glosis to be used to represent the data in semantic format, we needed to transform the Glosis UML into a kind of suite of ontologies. And we did that in some kind of semi-automatic process, which basically did some kind of automatic transformation based on some configuration. But this was accompanied by, of course, a lot of pre-processing, but mostly a lot of post-processing activities that we had to carry out in order to align the outcome of this automatic process with the SOSA, SSN, and ISO ontologies that we use as a base, which are basically the most commonly used and are standards to represent observation information. So we did a lot of that. I will go into details on this. But talking a little bit about the tool, we use a tool that is called Shape Change, and that did this initial transformation that implements some ISO rules for mapping ISO geographical information UML models into our ontologies. So you just need to make some kind of configurations files, how you want to map the resources or the information in the UML, and how is this mapped into the target ontology that you are producing. So this is like very simple approach. Well, not very simple, but it's like a very straightforward approach. Then you need to make some kind of configuration. There are different rules that you need to identify how this transformation should look like. But at the end of the day, this just gives us a little bit of let's say benefit in the sense that we don't have to code everything from the UML, because we already saw that there are like hundreds of concepts and terms. So it's a lot of information there. So instead of doing this manually, this gives us a starting point already in the old ontology world. So the output of this shape change ontology transformation was basically, in a very simple words like that, all the spatial types, the UML classes, were modeled as OWL classes. So that was out of the box. The container classes, they were also modeled as OWL classes. And all the properties encapsulated in the container classes were modeled as object properties or data properties with the domain of the container class. So that was like the straightforward transformation. But of course, this was not the target ontology that we can, that we wanted to produce. So this is, of course, not aligned with the best practice in how you are representing observations with the SOSA SSN, which is, like I said, a standard from the W3C OGC. So we had to do a lot of things. So that's the post-processing part, which basically did the following step. First, all the container classes were removed because they were just used as a kind of encapsulation, like I said at the beginning. So they are not real classes. So they were just used by Kati and Tomas in the UML model to encapsulate, to make some kind of grouping of the different properties. But they are not real classes. So they don't need to be in the ontology. Then all these container classes properties were transformed and aligned into SOSA SSN. And we found basically 5 different types of properties: the category observation type, measurement types, character stream types, complex observation, and troops observation. For all of them, except from the character stream, were aligned to the SOSA SSN. And they were defined as subclasses of SOSA observation. So I will go into details how we did that. So basically, these properties were modeled as subclasses, as I said, but they were restricted with a set of axioms, OWL axioms, which are used to specify exactly the semantics of what kind of information you are representing here. So we basically use these kind of properties. So basically, the has future of interest, which specify which is, basically the future of interest of this observation, right? The has result or has simple result that says what is the result of this observation and what is the observed property of this observation. So we did a restriction, like very clearly and explicitly define all the restrictions of for each of those property, what future of interest is associated, what kind of results we expect, and what are the observed properties for this particular observation. So the first restriction, like the future of interest, is uniform across all the classes of the SOSA observation. So basically, it connects the subclass that we generated to the associated spatial object. So the plot, the site, the profile, etc. So this is, like I said, how you associate the future of interest of the observation. The second restriction, this has result or has simple result, is represented differently depending on the result type. And we have basically 3 types of results: string values, code list values, and numeric values. So depending on the result type, we generated these axioms differently. I will show you some examples. And the third restriction, which is the observed property, is basically linking the observation with the associated property that was observed. And this property is defined as an instance of the observable property, right? So there are a few cases, though, that the observed property is linking not to an instance, but is linking to a code list. So it's not just like a specific observed property, but it's a potential classification of these properties that are observed by this observation. So for this, we needed to create also code lists. So going to the more details, for example, for results with the type string, it was the simplest one, the simplest scenario. We just had to say that this has simple result is used to restrict the values to a type of XSD string. So this is how you say in our world that the type of information that you are going to have here will be of type string. So here you can see how this looks like in the ontology editor tool that you can use to visualize the ontology. So you can see here in the middle, it says has simple result only XSD string. So we are saying here, for example, for this particular property, which is erosion area affected, we are saying that the feature of interest is a plot or a site. We are saying that the result should be a string. And we are saying that the observed property is the erosion area affected property. That's what we are saying here. And this is coming from the UML, of course. All of this information is coming from the UML, But also we had to take into consideration a lot of Excels that were produced by Katy and Tomasz that were collecting like the kind of code list that I will mention in the next slide. So for results with type numeric type, it's similar. The only difference is that instead of having has simple result, we are saying that has result, and this goes to some kind of numeric value object that you can say not only that is, for example, as an integer or that is a float, but you can also say what is the unit of measurement. So you can say, for example, this is, for example, for soil depth, this is the unit of measurement of the result should be in centimeters, for example. So this is how the numeric types were represented. And then for the code list, so this is the most complex one. So basically, you have to say, first of all, that the has result is associated to a kind of auxiliary class that is representing the code list values. So for each code list, we model like first a class, which is like a subclass of concept, as concept, and also a concept scheme. So these are like the most common way of representing code lists using SCOS vocabulary. And we connect them between each other. So the class and the SCOS concept scheme. And then for each value of the code list, they were modeled as an individual of this class, but also they were part of the concept scheme. So that's how we are making the connection there. And finally, the class is further defined as an enumeration of all the individuals that we just defined. So here, for example, in the slide, you can see their erosion degree. And the erosion degree says that has resolved this code list. And then this code list, for example, is all the different values for erosion degree. And we have the instances here. So code list value E, code value M, S, and V. And for each of them, we say, for example, the E means this is extreme substantial removal of deeper surface horizon. We are saying that this is a part of the schema, concept schema here. And we are saying that this is an instance of the class, as you can see at the bottom here. So this is how we are representing all the code lists. And this was a very, I would say, like the most difficult part, just to make sure that all the different values that we collected from the Excels, from the documentation that were provided with the UML were properly encoded in the ontology. So at the end of that, after that, we had to make some alignments, additional alignments with the ISO standards. And not only the ISO 28258, but also with other ISO, it's called the TC200 standards. These are existing ontologies. But the only problem is that the ISO 258, this doesn't exist as an ontology at this moment. So we had to create our own, this ontology, at least like basically all the required elements of this standard, we had to represent them in an ontology, in the ontology as well. But as I said at the beginning, this has been done in modules. So that's very easy then to separate all the different pieces of the ontology. Additionally, we had to make alignment between the ISO SOSA SSN components and the GeoSparkwell elements as well. And of course, at the end, the ontology was checked for consistency using the reasoners. This led us to identify some mistakes, probably some typos or some things that we didn't foresee at the beginning. So it was very important because when you are building like large ontologies, sometimes you are losing, of course, or making some mistakes or some typos, right? So this is very important. So this is in the right, you can see how the ontology looks like, the modular architecture of this ontology network, let's call it. So you have the entry point, which is Glosis main. And then you have a module for each of the main spatial types, which was plot, observation, profile, horizon, surface. And then you have some additional modules, one for the ISO 28, one for the code list, one for common. So this module common is just extracting, like factorizing all these elements that are reused across different modules. Instead of repeating this in each module, we factorize them here. And then, of course, you can make additional extensions like this. And all of them are coming from the SOSA SSN. So that's how you can look like. You can see at the architecture of this ontology network. Important is that the ontology is published using persistent identifiers, the W3ID. The first extension of this is already on the way. So that's the final architecture. And just a brief overview of this, more visual, of the final ontology. So on the left, you see here some initial part, like the future part of the ontology, and all of the different elements that are here. So you can see the horizon, the layer, the plot, etc. So this is, and as you can see here, this is coming from the ISO, and then going into the glosses, because we are going, of course, like I said, from aligning to these standards. We are producing proper documentation for all of these modules. So it will be something like this. We have some already on the way, but it's still a lot, many of them. So it's still not finalized. And the ontology is published with a license of attribution non-commercial share alike 3.0. Just here at the top, you can see actually some statistics or metrics. So you see the ontology has over 9,000 axioms. It has 325 classes defined. And then in terms of properties are not so many. So object properties like 50 and data type properties 19. So the most important are the axioms, the classes, and of course the individuals, which are necessary to define the code list. So that's more or less the statistics here. So how we are using this result ontology? So basically, as I said at the beginning, as part of this project CAU Soil, we are generating linked data. And in order to do that, we are implementing some kind of linked data pipelines. So these linked data pipelines are taking some sources, for example, as shapefiles or our CSV, JSON, and transforming them into linked data and then connect them. So that's the idea at the end of the day. So to have some kind of integrated data. And all of them, of course, will be based on glosses. And this is where the glosses comes into play here. So I cannot go into detail of all this process, but it's basically just an overview, like you have an idea here how this is actually being used, is currently being used. So starting from the data, the whole transformation part, and then the analysis and visualization with some kind of nice interfaces. Actually, just to say that there is already implementation of this pipeline. So it's not just conceptual thing or something that is manually carried out, but it's there are some tools that we are developing in order to allow the automatization of this process, of these pipelines. So we have like a command line tool for this already in place. Still, of course, some extensions are needed for support additional pipeline, but some initial pipelines are already supported, like pre-configured pipelines, but also there is a possibility to have like kind of generic pipelines. So then you have the possibility to customize the mappings and the target ontology, etc. So there are these kind of possibilities, but also there is a web service in place for that, and that we are working. This basically just wraps the command line tool and exposes all the functionality via a RESTful API. And this is deployed in a PaaS environment that connects with other components like storage, security, queue management, and other functionalities as well. So just to conclude here, our next steps are regarding the ongoing transformation of the soil data sets like Luca, soil databases into linked data in order to integrate them and connect them with other relevant data sets, including data sets from the linked open data cloud that I showed at the beginning. The implementation of dedicated soil pipelines, soil data pipelines to automatize this process that I mentioned, just extending this implementation that I just showed. Finalize the documentation of the Glosis ontology, serve the ontology also from the Glosis domain. So this is also now carried out, and potentially create alignment with other relevant ontologies and vocabulary. So that's with that I am finishing. So thank you very much.
Okay, thank you so much. So I have probably a very basic question. When you were talking about, that was a fantastic presentation. Thanks so much for that. And I'm actually going to stop the recording right now.